In this video, we're going to talk about electromagnetic radiation as it applies to a chemistry class. But first, we need to talk about what energy really is. Energy is technically defined as the ability to do work. In physics, work is defined as a force that's applied over a distance. We can think of this as pushing a box with a force some distance x. In this situation, we would define work as literally the force multiplied by the distance. Molecules also have the ability to do some pushing if you can trap them in a container. The faster the molecules move on average, the higher kinetic energy they have. The formula for kinetic energy is given as 1/2 the mass times the velocity of the particle squared. The more kinetic energy the particles have, the more ability they have to push the parts in their container. Objects are also said to have potential energy, or the potential to move from a position. Consider a box that is lifted up into the air. In this case, the force needed to move it is its mass times gravity, and you would multiply that times its height. This would get you the work. Now that we have a few simple ideas out of the way, let's talk about how energy applies to electromagnetic radiation. The term electromagnetic radiation sounds really fancy, but it's really well suited to describe what's going on. We all know that positives and negatives can attract, which would be a pull, or they can repel each other if there's a positive and a positive next to each other. In that case, we can think of it as a push. Magnets can also attract or repel each other, depending on if you have the north and south parts of a magnet facing each other, where this would attract, or opposite to each other, where they would repel. Both of these types of forces, electric forces or magnetic forces, apply over a distance, but they are still a type of energy, even though you cannot see them. Electromagnetic radiation is made out of oscillating, or things that go up and down with a pattern, electric and magnetic fields that can travel through the vacuum of space. The best representations that I've seen in classes or textbooks model this type of radiation like a wave. They'll draw one wave with little arrows representing the strength of the electric fields, growing in one direction, then lessening, then changing directions, growing and lessening, over and over and over again. Then, these really good representations draw a magnetic field also oscillating, but in a plane that is orthogonal to the original drawing. If that's a word that is kind of difficult to think about, you can think of making a T with your arms. The magnetic fields also oscillate. So, if you haven't guessed, electromagnetic radiation is pretty weird. What you need to know for now is that it is a type of energy and that it behaves like a wave. This means that we can model electromagnetic radiation with mathematics. To talk about this type of energy, we'll need some vocabulary. First things first, the wavelength of any kind of wave, but especially electromagnetic radiation today, is the distance between two crests or troughs, one complete oscillation. We generally measure this quantity in meters. If the value is reported with an SI prefix, please make sure that you convert it to the base unit of meters before performing any calculations. This is especially common in the visible light range, in between around 400 roughly nanometers to around 850. Please don't quote me on that. Nanometers. You definitely want to convert those into regular meters first before doing any math. The next quantity we need to talk about is frequency. In some textbooks, they use F for frequency, and in some textbooks, the Greek letter nu. The Greek letter is a little difficult to draw, so I'd understand if you want to use the letter F. Frequency describes how often a complete wave passes through one point in space. We can use the formula frequency equals the number of cycles or complete wavelengths per second. It usually has units of 1 divided by seconds, which are sometimes called hertz. The last thing we need to talk about is the speed of a wave. In general, this is the frequency multiplied times the wavelength. If you perform that calculation, you'll end up with units of 1 divided by seconds multiplying times meters, which you get you units of meters per second, which we know from physics class is the unit for velocity or speed. For electromagnetic radiation, the value of the speed is always the speed of light. This value has been experimentally determined to be around 3.00 times 10 to the 8th meters per second. Please make sure, again, that you always do your calculations with your wavelengths in meters. It won't cancel with your speed of light equation if you don't. Now, last things, we can write this relationship even better if you use the letter for the speed of light, which is the letter c for some unknown and crazy reason, and you have the speed of light is equal to the wavelength of the electromagnetic radiation multiplied times the frequency. Finally, we need to incorporate that idea of energy to our waves. There are some pretty famous scientists that came up with a way to describe the little packets of energy that electromagnetic radiation provides using these values. Energy is equal to a constant called Planck's constant times the frequency. Our textbook generally defines Planck's constant as being equal to 6.63 or 6.626 times 10 to the negative 34 joules times seconds. You can think of this guy as the slope in between a plot of energy versus frequency. If you substitute in our frequency into our energy equation, we can rearrange our formula to get an equation that incorporates the wavelength of the wave. Though these concepts are a little abstract, if you take a deep breath and use these equations to conquer any question about electromagnetic radiation with regard to the waves. In our next lessons, we can see how we use electromagnetic radiation to probe the atomic and subatomic worlds.